Great, so thank you for the invitation. Today I'm going to speak about the symplectic capacities of P products. This is a joint work with Yaron Ostrover. So let me start by reminding you what is a symplectic capacity. So it's a way to roughly measure the symplectic size of subsets of R to N. So we wanted to a function which assigns a number for each subset, which satisfy these four properties. Well, the first is if U is contained in V, we want its size to be smaller. We want it to be invariant under symplectic homomorphisms. We want it to be homogeneous with respect to multiplying omega, or symplectic form. And we want the capacity of the ball and the cylinder with the same values to be equal. And in fact, the existence of a normalized capacity is non-trivial and is equivalent to Gromov-Zahn squeezing. As you can define the Gromov-Witz capacity, which asks what is the biggest ball you can symplectically embed into your domain, and the cylindrical capacity, which asks what is the smallest cylinder you can embed your domain into. So that is the main object we will talk about today. And throughout the years, there has been many symplectic capacity defined. And it turns out that many of them are equal when we look only on convex domains in R2N. And moreover, they are equal to the minimal action over all closed characteristic on the boundary. And there will always exist closed characteristic for convex domain. This is somewhat non-trivial because convexity is not a symplectic property. So it's not clear what is the role of convexity here. And in fact, there is even a stronger conjecture which asks whether all capacities coincide when we look on convex geometry. So we call this minimal action of closed characteristics the Ekman-Doppler-Zehnder capacity. And capacities are very hard to calculate, and we know what their value only on selected examples. But in recent years, there's been attempts to try and calculate them for convex polytopes in R2N. So a few years ago, I came up with a combinatorial formula for the EHZ capacity of convex polytopes, which allows you to find the value accurately in a finite time. And there's been also work of Chaides and Hutchings, which finds all closed characteristic up to a certain Conley-Zehnder index in R4. So even though we have these algorithms, they are very limited as if the polytope is complex, then its running time is growing exponentially, so you cannot calculate it for complex polytopes. And also, there is still a lot unknown here, even in this narrow class of convex domains in R2N on capacities. So one important question in this field is the Viterbo conjecture, which states that out of all convex domains with the same volume, the ball have the biggest capacity. So if we denote the systolic ratio as the ratio between the capacity and the volume with the right power and constant multiplication, such that it would be one homogeneous, and the systolic ratio of the ball would be 1. This conjecture translates to as being if the systolic ratio is always smaller than 1. And now this conjecture is very hard, as it's not true for star-shaped domains, and it's also not true for dynamically convex. So somehow convexity plays a crucial role here. And it's what is known to this day about it is that it holds up to some constant independent on the dimension, and that it holds also in some small neighborhood of the ball. So one is a maximum somehow, local maximum. And also an interesting relation is to convex geometry, which states that the Viterbo conjecture would imply the Malan conjecture for, which is a conjecture, famous conjecture in convex geometry, open for 80 years already.
Sorry, when you say it holds near the ball, what topology are you allowed to perturb in?
So we look on contact forms on S2n-1 and C3 neighborhood of.
Sorry?
C3 neighborhood of the.
C3.
Yeah.
Okay. Thanks. Thanks.
Okay, so our small step towards approaching this conjecture is trying and show that if the Viterbo conjecture holds in high dimensions, it holds in all dimensions. So it's in two parts. The first one states that if it holds in some dimension 2n, then it holds for all dimensions smaller to n. And the second part says that if it holds up to some function of n, and the function goes to 1, then it also holds for every dimension. This type of argument is sometimes useful in convex geometry, and as things tends to be sometimes easier in higher dimensions. And in fact, for example, the best known constant today of the Malan conjecture was proven up to some function which goes to 1, and hence they knew the same sort of argument works in the Malan conjecture. So we use this type of argument to show the best known constant today in Malan. So these two, we hope that it could be useful. And the way to try and approach this type of question is to start from some k and try to build from it some domain in higher dimension with a smaller systolic ratio, a bigger systolic ratio. So a natural approach would be to take k times k. However, this is not successful, as if you look on the ball and you take its Cartesian product with itself, then it's no longer a symplectic ball. And its systolic ratio would be smaller, strictly smaller than 1. So you cannot take just a Cartesian product, just a symplectic Cartesian product. So you need something else, and it turns out that that something is a p-product. So what is a p-product? We take two domains, k and t, in two different copies of R2n embedded in the same large domain. And we say that x comma y is in the p-product of k and t if x is in, say, alpha k, rescaling of k, then y is in beta rescaling of t, such that alpha to the power p plus beta to the power of p is less than 1, then it's in the p-product. Right, so if we take the one product, it is the convex hull of k times 0 and 0 times t. And if we look at the infinite product, then it's the Cartesian product. If P1 is smaller than P2, then the P1 product is contained in the P2 product. Right? So we have a sequence of P products starting from this convex hull and ending in the Cartesian product. And some examples are the ellipsoids are two products of segments, and the LP balls are p-sums of segments of equivalence. Okay, so some, again, examples. So the first line here is the p-product of a triangle and a line. As you can see, it increases to the product of the two. And here the second is a p-product of a line and a circle, a disk. And the two product of the line and the disk is indeed the ball. Okay, so in order to understand how the systolic ratio changes under p-product, we start by understanding the volume and the capacity. So it turns out that the volume of the p-product is an easy dependence on the volume of K and T, and this is just this easy lemma, where this is the gamma function. And the capacity is turns out to be the minimum between the capacity of K and T if P is larger than 2, and this formula is otherwise. So the way to see this theorem is to understand the dynamics on a p-product. We can see that this value comes from a closed characteristic, which is just the minimal closed characteristics on K times 0, and C of T comes from 0 times the minimal closed characteristic on T. And this value of P smaller than 2 comes from rescaling of the minimal orbit on K and a rescaling of the minimal orbit on T, where we move on both of them simultaneously. And these 3 orbits are always exist for every P. However, for P smaller than 2, then this is the minimal, and for P larger than 2, it turns out that this is the minimal one. Okay, so now we can say something about the systolic ratio, and we really have what we wish, that the systolic ratio of the p-product is always smaller than the multiplication of the systolic ratio, and we have equality if and only if the capacities of K and T are equal and P equal to. For P larger than 2, this seems relatively easy to see, because as P grows, the volume grows and the capacity remains the same. So we have the systolic ratio of the P product is smaller than the systolic ratio of the 2 products, and that is smaller than the multiplication of the systolic ratios. So for P larger than 2, it's easy to see, but for P smaller than 2, it's a bit more tricky, because we do not have monotonicity here. It could be that for P smaller than 2, the systolic ratio would be larger than the systolic ratio of P, but this entire inequality remains true. Okay, and in fact, this shows what we wish to show, that if we know Viterbo conjecture in up to a constant going to 1, then up to a function going to 1, then we know it's in every dimension, because we can take K times 2K times 2K as many times as we need, and we get that this is smaller than almost 1, and so it is equal to the systolic ratio of K, and so it also holds for K. So this is, in fact, finishing up the proof. And we really need this p product because we use this for the 2 product. So we couldn't do it with the Cartesian product. Okay, so and now that we understand the dynamics on the p product, we led to this conjecture on higher order capacities. And here CK is referring either to the Ecklandhofer or the Guth-Hutchins capacities, which are conjectured to be equal. And we conjecture that it equals to the minimum between I plus j equal k of this for p greater than 2, and the maximum if p is between 1 and 2. And in fact, these all of these quantities are coming from some closed characteristics on the boundary of k, of the p products of k and t. Which is a combination of orbits in k and t. And this conjecture generalized some known result for the Cartesian product of domains and p products in some special cases. Okay, and in fact, the beautiful formulas of Guth and Hutchins for the cases of convex and concave toric domains allow us to show that these formulas indeed hold for convex domains, convex toric domains if p is bigger than 2, and for k and t concave toric domains if p is smaller than 2. So in that cases, we know it as well. Okay, and a somewhat application of that conjecture would be that to try and understand when can a domain be represented as a p product of 2 other domains. And more specifically, we asked if a ball can be p-decomposed into some domains. So if the conjecture we've shown holds, then it means that any symplectic image of the ball, if it can be represented as k times p-t, then p must be 2. So for every p different than 2, it cannot be. And moreover, we have that if p equal 2, we have that the entire spectrum of higher order capacities of k equals to a spectrum of a ball with the same radius we started in the appropriate dimension, and the same for t. And even though equality in the all higher order capacity doesn't mean that you are a ball, it doesn't mean if 2 domains have the same higher order capacity, it doesn't mean they are equal. But in a ball, we have reason to suspect that it might be true, or at least they share many properties. So here the model is to try and show that if a ball can be p-decomposed, it can only be the trivial decomposition to a 2 product of 2 balls. So why we suspect that if you have the same capacities as the ball, you are a ball, is it because if all n high order capacities are equal, then you are a symplectic zone, which is saying that through every point you have a closed characteristic with minimal action, and a ball satisfies that. And we know that in our flow, symplectic zones are balls, and in higher dimension they are maximizers of the systolic pressure, local maximizers of the systolic pressure. So indeed, we have reasons to thinks that this might say that the ball can be only decomposed to balls, trivially. So, okay, I'll probably stop here.
Thank you very much, Pazit. Any questions?
So what your first theorem about the Viterbo conjecture being true in different dimensions, and so if I understand well, you have the same result for the Malher conjecture as a consequence.
So you're talking about this theorem, right?
The first, yes.
Mm-hmm. So in Malher, you can see it more directly. You can take just the Cartesian product of domains and you would get something similar.
Okay. Mm-hmm. Thanks.
In the last theorem of the decomposition, if one of the two you would allow to be star-shaped, then can you say what can you make this way as a p product of one convex, one star-shaped?
Again, everything he said here is coming then the assumption that this formula holds, right? So if this is just using this, right?
So you say you can actually remove convexity completely. I'm not sure. So there is a theorem.
This is a claim on higher order capacity, right? If you assume this formula, then you can say that if some p product have a spectrum of a ball, then both domains in the product also have a spectrum of the ball.
But in which class of domains? You assume domains to be what a priori?
In which domains this formula holds.
I see. Okay. Okay.
So for the proofs, you have a kind of probably for these spaces a good candidate of action shortest orbit, and then you must show that he is the shortest, right? Is this the proof?
Yeah.
And how do you do that to show that there is nothing shorter?
So you can just so you understand the dynamic very well. It's not in terms of the dynamics of K and T, right? You can understand the dynamic of the product very well. So you can actually see that it's the minimal, but also you can solve it some optimum, relatively easy problem on using Clark's dual action principle.
Okay, you dualize.
Yeah.
Okay. Okay. Thank you.
Sure.
Any more questions?
Could you please repeat, so this phase transition at p equal 2 in your formulas? So what is the reason for it in geometric terms?
I don't know what to say in geometric terms, but in terms of the dynamics, you can see that there's a phase transition on how fast the other dynamics goes while you move at the first one. So it really, in two, they sort of move together. This is why, say, for ellipsoids, you only have combinations when the radii are irrationally dependent. At two, they move together, and when the bigger is in two, then it moves very slowly. So the T can close without nothing happening in the K. And when P is smaller than 2, then the K moves really, really fast. So you are very impacted by what happened there, right? So say in this formula, the difference here is because of the Conley-Zander index. Like it would be the other side would impact you differently. Sort of what happens in K while you move in a closed characteristic in P changes. I don't know if it was clear.
And what is regularity in P? So it's continuous, but can you say a bit more? Or?
Oh, so I probably should have said that in P equals 2, when we look at this as mean of maximum between Ci of K and Cj of T. And here we have maximum of minimum between Ci of K and Cj of T. And in fact, they are equal, this mean max and max mean. And they are equal also to the kth element in the sequence of Ci, K, Cj, T, arranged in non-decreasing order with repetitions. Right? So if you just take all the series of the higher order capacity of K and T and arrange them, then you take the K element, and that would be the CK of the two products.
Thank you.
Okay, guys, I think we can thank Pazit again. So thank you very much for the very nice talk.